Hey guys, welcome to my stream. So a couple minutes ago I was working on a way to optimize, be able to, I tried actually implementing a way to take the debugger's trace output and stick it into a circular buffer, into like a ring buffer, hoping that I could keep, say, the last n commands in a buffer, and then when we break into the debugger, dump the whole thing. And I was unable to get that to work well, because it turns out, we looked at the profiles, that the biggest cost really comes in the form of doing the string formatting. So I thought about it yesterday, and I'd like to keep working on this. My idea here is to try something else. We're going to try and rather than actually do any kind of formatting, just store enough information, like binary information, about the instruction and perhaps decode 1 or 2 memory addresses. I'm not sure yet there, we'll see. And then basically just do the formatting lazily and on the fly when we need it. So let's say we break into the debugger and we want to show the last n commands. It's only at that moment we're gonna do the disassembling and getting the values. Now it's a bit tricky because I think I'm gonna end up losing some information, because right now the fact that I do it like immediately when I'm about to execute an instruction allows me to just say like, oh, I can read the current value of any address as it is right now, whereas now I would have to kind of think of which addresses to store for the future, which values to read from those addresses right away and store them for the future. So there's going to be a little bit of trickiness there. So I'm gonna try and see where it brings me. Hey Blue Dragon, thanks for joining. So yeah, I'm gonna just kind of hack at it, and we'll see where this takes us. So I'm gonna actually, so I have here this is like a little branch with a commit I made from 2 days ago. I'm gonna reset or check out master here, and we're gonna just go back and we're gonna start from here. The first thing I'm gonna do is I'm just gonna see, like, if I was to store just a ring buffer of like what I think would be enough data for what we need for doing the trace, how does that affect performance? So we'll take a look at that, and then we'll go from there. So let's build. Should work now. So Blue Dragon asks, so what was the problem? You were storing process strings for every op and that was slowing you down. Yeah, exactly. So like, let's say we break here into the debugger and we turn on trace, right? And we step, right, like this. See, like all this output here for the current instruction that gets executed. Like if I make this a bit wider, there you go. See, each one of these lines, this here is me basically doing printf like style formatting to output all of this in the format you see here. This is disassembling the instruction and then printing the mnemonic and the instruction itself. And then here we have this, what I call the comments section, which is the kind of helpful section where, depending on the instruction, I try to output useful information. Then here I do some more printing where I say, like, this is the number of cycles the instruction took, followed by the values of all the registers and the flags here at the end. Oh, Blue Dragon says, ooh, that overlay, haven't seen it in a while, it looks so good. You know what, then I'll just really quickly give you a little demo here. Actually, this game won't run, but let's show Minesweeper here. So do that. And then that's the overlay alpha. I should probably play with the controller. But anyway. So like if I bring the alpha down, and I can also play with the darken speed scale. You can have like really long trails. I think you saw that. This looks kind of crazy, but or we can have like no trails at all and have heavy flickering, or like something in between. So there you go. So that's basically the state of affairs right now. Okay. So yeah, let's work on this this debugger stuff here. So one thing I'm gonna do, this is something I really like about Git extensions, is I can take, say, a file or sections of a file, and I can cherry pick those parts from another commit. So I'm going to just cherry pick this file's change here, which will just bring in the circular buffer header file into my working directory. So there's circular buffer. So the trick is going to be, I have this instruction type here. So I'm going to be storing this for sure. That basically keeps track of which op we're running and which page it comes from. And it'll store up to 3 operands, and I have this read instruction. So that's what I'm currently doing when I disassemble, is I do this read instruction here. And then after that, I use that to then do the disassembly. But what we'll do instead of disassembling is we'll just do the read instruction and add it to the circular buffer. So I'll start with that, make sure that that works, that is fast enough, and then we'll see after that. So I think for now I'll hijack print op for this, and maybe it's not necessarily the wrong thing to do, but I'll just do it in here for now. Print op. So we read at the PC, pass it the memory bus. Okay, so that returns an instruction, and we'll make a circular buffer of those. Actually, we'll make a, what should we call it? Okay, actually, let's just start with instruction first. We need to call init on this. No, I'm not getting my autocomplete here. Ah, that's why. Okay, so we'll just push that back here and we just won't print anything for now. And then post-op will do nothing for now. Okay, so what is it that doesn't like? Is copy disabled for std array? It's saying here that assignment is deleted. It was implicitly deleted because it has a data member. Oh, right, because it's of the reference here. Oh, yeah. Okay, so we can't copy it because it has a reference type, but we could, I think, without changing too much code, use a reference wrapper here. I might have to also change the way we initialize it. Okay, forget reference wrapper. What we'll do is we'll have to turn it into a pointer. Which means that everywhere we do CPU op dot is going to have to become CPU op arrow, which really sucks, but I don't know if there's that many really. Not too many. Okay. Match word, match case. Current document. Okay, 22 instances. Okay, so that built. So we turn on the trace. Okay, so we don't even notice the hit. I'm looking at the frame rate up here. It's like we're averaging around 510 or so frames per second. I say 505. Anyway, around 500. If I turn off the trace. Okay, actually now there's more going on in the game, so it's a bit slower, but yeah, it's around the same thing. And let's see if we actually have something in it. What did I call it? Instruction trace buffer or something? Alright, so there are, yeah, we can see that this, basically this is the buffer of the last 1,000 instructions. You can see that there's a whole bunch of like instructions in there. There's an opcode, a deck, and then they have potentially operands with values in there. Okay, so that's pretty good. Now, start with that. Let's see. Instruction trace info. I guess technically I could do a move here, although I'm gonna get nothing because it's totally a value type right now, so whatever. Yeah, even stood array here, he'll have to copy it, so okay, we'll just do this because I'm gonna be adding more stuff to the instruction. So now say I have that, and I'm accumulating it, and I would like to try printing, let's say, the last n instructions when we break. So when we do a break into debugger, what I'll do is I'll actually make that an instruction we enter ourselves. I won't do it automatically. So, and I think there's something in GCC for that. Just give me a sec. List. It's not exactly that though. It's really about trace. Because list is really about showing, let's say, a listing of the source code, whereas here we're really talking about trace. So I think we're going to do our own command related to trace. You know what, I'll just start with T for now. Or maybe like by default we'll show the last 10 if you don't specify anything. All right, so now yeah, I think my ring buffer was never meant to just read from. It was meant to push and pop from, so I don't even have a way to access the values. without popping them, I mean. I have pop with into a destination with number of values. I'm gonna do a little hack, and then we'll do this right after. So what we'll actually do for now is we will pop the values, and then I'll actually push them back. Ken gives me a laugh out loud clever. Yeah, so I mean, it's not that clever there. I don't really want to do this, but I'm looking at this code. I'm like, yeah, this is like tricky. I remember when I wrote this was tricky to get right. And effectively what I want to do is I want to do the same thing without actually modifying the pointers and stuff. But see, like, this code kind of is written so that it depends on the fact that the pointers are moving, right? So in order to fix this, what I need to do is I need to store the values of my pointers, and it's mostly indices there. I think that's what I'm using. No, that's it's pointers. So I need to store pointers in local variables, and then like do the work with the local variables, so I don't actually modify the underlying representation. So yeah, it's peak though because it puts it back immediately inside the peak. It's not really a borrow, right? But internally it's not efficient, you know. So yeah, and I don't think, do I have a pushback? Yeah, actually I even have a pushback with the number of values, so that's hilarious. Oh yeah, you know what I'll do? I'll do this. None values actually read. There we go. So this is a super big hack, but basically we tell it, go ahead and pop back that many, or attempt to into destination. Then push them all back for the number we actually were able to read, and then return the number actually read, and our destination has those values as well. So it's really bad, but it should get the job done for now. Hopefully. All right, so now we have ostensibly what we want here. Let's just see if this even like works. Oh, and actually I'll do this in debug. Okay, so turn on the trace, we'll run it for a little bit, we'll stop, and we'll say T. Okay, let's just start with T. Okay, so come here, tokens is 1, so N is 10. We build a buffer to hold 10 values, and then we say peek back. We pass in our pointer. So here we're gonna do our pop back. Now, if I look at this, so here's our buffer. It has 1,000 in terms of capacity, and its size is 1,000. So after this pop back, I expect the size to actually become, what do you say, 10? So 990. Oh no, that's it. I don't change the size. It always remained fixed. It's just I move pointers around. Okay, it looks like I actually did read 10 values, and the destination should contain those values. Let's see. Well, it contains at least one. From the outside, we should be able to see it. Okay, there we go. LDA, SDA. So we have 10 values. Let's hope those are the real values. And then after that, we push them right back. So one way we can check is if we just redo it again, do we get the same 10 values? So let's check. We're gonna push them back. So okay, this guy's still still visible. So like if I copy these, like that. And then let's run T again. I have an empty buffer. Okay, that doesn't look right. Okay. What about the third time? Okay, so it looks like it's one more. No. What? Is there any relationship here? be pushed. Well, I guess we'll debug it. So we want to pop 10 values. So what does that change in here? What we'll do is we'll just take a snapshot of the values just in this buffer here and see what changes. So I'll do this in beyond compare, so I can just see what happens after that. So I say copy from mfront. Trying to remember what my contract is with this class. Right, because normally I push to the front and I pop from the back. Is that right? No, sorry, I push to the back and then I pop from the front. And I had a way to push back one value or many values. I wondered if I ever even tested pop back, now that I think about it. I think I only ever used pop front, so it's very possible that I wasn't using pop back. It's bothering me that I'm copying from front here. I'm gonna try something. I'm pretty sure my pop back is incorrect. But the pop back single value seems correct. So what we'll do is we'll kind of cheat. Shouldn't this be the same here? Alright, so let's pop back as many times as we can, and then we break. Then we'll push them back. So this I'm pretty sure works, so we'll see. And then actually I would be the number of values read, I think. Yeah. Let's see. Okay, so let's see. The buffer got nothing. Oh no, that's right. That's why I didn't have this if here. The back pointer can be equal to the front pointer in the non-wrapped case. This code is very confusing to write. Actually, I need to run a little bit. Okay. Okay, so we have values. Okay, so this worked, except now the values are in reverse, which actually, that's interesting actually. So is that what my pushback does? It adds them in reverse. I suppose that's, does that make sense? Oh yes, of course it makes sense. Because I'm popping them in reverse, right? Yeah, I really need to fix this and do it properly. Where is it again? Peek back here. So what I want is I need to pop them back in the opposite order. So num-values minus I minus 1. Yeah. Okay, so now we should be getting the right order. Turn on trace, and let's see what we get. Run it again. And there we go. So the last, so ostensibly these are the last 10 instructions that ran, and it's repeatable. So I'm going to put here to do. It's here anyway. Fix pop back for multiple values and rewrite. No, actually what I want to do here is implement peek back without popping and pushing. And I do need to fix the pushback of multiple values, because that doesn't seem to work. Because I'm just looking at the code here, and it's like when I'm not wrapped, front is behind back. But that's it. Oh, no, sorry, it's not pushback that I had to fix. It was this pop back here. Like right off the bat, what seems to not make sense is the fact that I'm copying from front num values to read, whereas what I should be doing is copying from the back minus num values to read up to back. So I don't really know what I was thinking when I wrote this. Okay. That's okay, we can move on for now and we'll worry about fixing that later. So now that I have that, we want to be able to actually print those instructions that we just got into this vector, right? So to do that, we want to make use of our disassembly routines. So I'm gonna have to modify this disassemble op just a little bit, because right now it's doing the read instruction to figure out, but we want to pass it an instruction instead. And it's gonna need to be reworked quite a bit, because right now it's gonna start reading from the memory bus, but the values it reads is gonna be all wrong. Okay, so instead of a CPU registers here, we won't have that. In fact, that is part of the state we're going to need. We want to have the state of the registers as well, right? So that's something that's going to we're going to have to add it to our, now that I'm looking at this code, what state those registers were in. We'll add that to our instruction trace info. This is also a value type, right? Yeah. Perfect. So we'll pass in instruction and we'll pass in CPU registers like that. Great. So let's go back to disassemble op. Don't need that, I think, right? Yeah. So we'll get the instruction out this way. Okay, so the reason why this is not working is I need to move the struct higher up. Let's put it near the actual instruction itself, or the struct up here. We have that, and well, the op is in there as well. For CPU registers, we can do the same thing. Yeah, right. So we do actually want the op address, but we'll do it this way. From the CPU registers, we can read out what the program counter is there, and then we can go and get I guess it's okay to read that from memory. Yeah, because those instructions don't move, so that's okay. Alright, so now if I go back to my T, now we do disassemble op and we pass it. We have to do a loop here. So we need the memory bus and we need our symbol table. Yeah. Okay. So let's see if this works. So we're tracing. Oh, right. This assemble op just returns a disassembled op. It doesn't actually do the printing. What were we doing this again? Ah, yeah. This is what we were doing. It's because I need to rename these functions. This is the actual printing function. It's going to kind of hijack it here. So what would we call this? Make a new one. We'll say something like this, add op trace info. So then actually the print op will be like print . So similarly now print op will take the trace info . Yeah, okay. And what we'll do is we'll say here auto op is equal to this. It will be a disassemble op, and we'll forward the disassemble op. I didn't even realize I had a one-letter difference between the two. So that will print it. Yeah, and actually I'm realizing now that I'm storing the CPU registers before the instruction, but really I would like to store it like I was doing before, as I was printing them after the instruction. So I'm gonna need to have like a pre and a post similar to what I had before, so that's fine. We'll fix that. Okay, so now where I have print op, if trace is enabled, okay, so we'll kind of need two functions. We're gonna need like a print last op for the single stepping case, which is what I have a bit of right now. And we're gonna wanna have a print op that takes in as a parameter the instruction trace info. Okay, we'll do this later. Okay, so I'm interested in print op. Almost there. Okay, so trace, continue, stop. Okay, so what's going on here? We're trying to do a print. We're saying disassemble this operation. Ah, but our trace info is invalid. Why is that? It's true that if I do T and I have nothing in my buffer yet, I have null ops. So I need to handle that case. But then why was I able to grab that many? Oh, right. I need to take into account what this actually returns, right? Then I actually need to iterate using an index because we can't go over the entire buffer. We don't know. I mean, I'm making it large enough to hold as many as we'd like to hold, but we don't know if that's how many we're going to get. So we need to use an index to go through it. So let's see now. So basically, if I have no trace yet, and I do T, it should return 0. Yeah, so we skip it. So that's good. Turn the trace on, continue, stop, T. Now we'd like 10, and we have 0. Why do we have 0? Oh, I know why. Because we're no longer doing the pushback because we're not calling add op trace info. That makes sense. And actually, instead of doing that where we were calling print op, I don't understand why I wasn't doing this already. Why wasn't I doing my print inside execute instruction? I always have a print op just before it. And I do the print post right after, so I really should have just been doing it inside here. Very odd. Anyway, okay. Okay, so now as we execute instructions, we are going to be adding them to the trace info. Yeah, so we got our 10 instructions, and now we're supposedly printing them, but we're not. I know why. It's because of buffered input. Did I like remove a new line when I messed around with this code? Let me go take a look. Oh, it's because I would do it in the post-op. I think this is actually working. Let's do it without breakpoints and let's just see how it goes. Turn on the trace actually. And there we go. That's the last 20 instructions, the last 5, the last 100, the last 1,000. And even if I ask for too many, I should not be able to. Or I should crash. I'm surprised because I would have thought that trying to peek more than I can should have returned. So maybe I'm hitting an edge case though. Like a boundary condition or something. So like if I say 1001. See, I got back 1,000. But I have a null instruction in here. What's I? 0 with 1. Oh, that's interesting. Oh yeah. Yeah, okay. I know what it is. Again, it's in my peek back. It's the way I'm storing into the destination buffer. I'm storing it at the end of the array and not at the beginning. You see that, Ken? I'm guessing if you're laughing it's because you know what the problem is. So how do I solve this one? Oh, you laughed when when I crashed and you thought I wouldn't. You know, I always do that. Go for the gold, you know. Sometimes it works. Sometimes, you know, you you code up a bunch of stuff and you're like, let's see if it works, and then it crashes. But it's okay, because it crashes, it asserts, and that's what I want. I don't want it to like silently fail, right? So don't worry about it. Let's see here. What's the right? The thing is, I don't know how many values I'm gonna get here, so it's kind of like a chicken and egg problem. I think I may actually do this the shitty way. So what I did is I'm writing into the array and I'm doing the pop back into the destination array in reverse. And when I'm done, I just reverse the whole thing from the beginning to destination plus I, and I being the number of values actually read. So if we do our same test, we turn on trace and then do like T1001. Despite the fact that our buffer is 1001 values, when we do the peek back in here, what should happen now is we will run up to here. Our destination buffer will now have all values in there except for the last one. So you see the first one is valid, but if we go to, oh, it's going to be a bit long. Oh, it doesn't show me the last. Okay. Oh, it says 1,000. Did I not type 1001? Oh no, it's the buffer I want to look at. Right. So yeah, that's it. The last instruction here you see has a null in it. But what we need to do now is we need to reverse from the 0th up to the 999th and leave the last one null. So like for example, LDS followed by JSR followed by BSR should be the first, and then the last one should be like this TFR here. So that's what the reverse is going to do here. And we push them back in the same, that's right. And then if we look now, I already forgot. LDS, JSR, BSR, I think that's right. And there's TFR at the end, yeah. So this should be okay now. And now we print them and we don't crash. See, and I do T10 and we'd still get the last 10 that we see here. So that's pretty cool, right? We're definitely a lot closer now to what I was hoping to achieve. Now, of course, there's what's wrong here is everything here on the comments side. This we cannot trust, because these are values that are being read from the memory bus right now, at the moment that I run this trace command. And so these are not the values that were in memory when this instruction happened. So that's what I'm losing right now. And in order to make this somewhat useful, I need to rework the comments. So, you know, like maybe based on the instruction, store. I'm not really sure how to do this. Like in many cases, I have this effective address. So maybe the key is to say, you know, for this instruction, let's compute whatever effective address we you know, that makes sense for this instruction, and do the read and store that piece of data along with our trace info. And then our comments here would not be able to give the same depth, the same amount of detail, but it would say, but you know, the value at the effective address was, or I can maybe store both the address, like an address and a value, and then just show those in the comments, and that might be still useful. Okay, so we still have a couple of more things to do. I'm just gonna go get some water. I'll be right back. Okay. I get so thirsty when I'm talking all the time. Alright, so I just have a couple of things I want to fix. So we have this add op trace info. So technically, only if trace is enabled do we really want to do this. What I'm going to do, similar to how I did for print op, I'm going to add a kind of a helper. Oh, no, I don't really need to do that. Add op trace info. I can do like this. If trace enabled, we do that. So we add the trace info, but this will be like before we execute, and then we do print post ops. This will be similar, except this will become I guess not really add in this case? Whatever. Okay, we'll do this a bit differently. I want to return this thing. No, I'm going to do this a little bit differently. Don't like this. We'll do something like this. So actually this here is not quite that. So we also want to store the elapsed cycles in our trace info so that we can print that as well. And then finally we'll have an add. In fact, that's just a pushback, so I'll just do that. Okay, so if we go to our execute instruction, and then finally, we push back the trace info here. So basically, we start off, every time we execute an instruction, if tracing is enabled, we go and create the instruction trace info here. In fact, maybe I won't do a create because there's like unnecessary copying going on here. I'll kind of do like a pre and post while I just pass it in. And then we push back. So basically, yeah, I like this. So we have a trace info. If tracing is enabled, we do the pre-op write trace info with this info, and then we do the, if after we execute the instruction, then we do the post-op write trace info. So that basically populates it with what we need. Now we can have our print op include the part that was missing. We'll be printing the elapsed cycles and the registers here. So let's see if that works. And yeah, that's not right. No, there's no return statements. Okay. All right. So this should build. So T does nothing because we didn't turn on trace. We trace a bit. All right, so there we go. We actually have, yeah, the number of cycles that elapsed. If we do, let's say 100. And actually, I wonder if color works. Yeah, the coloring still works. There you can really see how the coloring is slow. So I just printed 1,000 with coloring, and that's like line by line, because that's just the way coloring works. If we turn off the color, it's like almost instantaneous due to buffering. I can't do that kind of buffering and coloring at the same time, so with color it's a line by line operation. But still, it's kind of nice. Just try in release so we can get a bit further in the game. So I can even fast forward. And if I break, I can see the last 1,000 instructions. That's pretty cool. And what would be really cool now is that when I get like an exception for something that goes wrong, I should be able to trace what happened up until then. Now I put 1,000, but we should be able to do much more than 1,000. Like I should be able to store like I can even do, let's try 100,000. Let's see if we feel that. If I say, print me 20,000. Sweet. Okay, so that's cool. But now what I would like to bring back, so there's a couple things that I need to do to finish this off. So I don't think I'm going to be able to get the comments section working tonight. I need to think a bit more about how I want to do that. So what I'll do is first, we're going to not actually show the comments section, because we can't trust what we see anyway, right? I mean, I suppose I can leave it. It's okay. I know that it's not valid, and since this tool is for me, I'm not too worried. But what I would like to fix is, where was it? Print post. Okay, this is not being called, so I can get rid of this. would like to fix we can add T, and then we'll say So what I would like to fix now is the fact that I used to be able to, when trace was enabled, I like that when I say step, you know, with S, that I print the line we just stepped. So if I do break here, when I step like this, at least while stepping, I want to see the last thing we just traced, right? I don't mind it, like losing the ability to have it constantly dump, since now we know that we're, you know, doing it in the background. But while stepping, it is useful to see. And then if we continue, we don't need to do it anymore, and then we can use our T, you know. So see here, I used to do this print op here. And so what we'll do is we'll call it print last op. Yeah, I'm back to having this problem where I need to be able to, just peek one value. Yeah, so we'll do that. I should write one for single value, just like I have a pop back for single value, pop front, pop back for single value. So I need a peek back for single value. Okay. So if we are able to peek back a value here, which is instruction trace info. And then we would like to display it, which is actually what this print op does here. Yeah, I like when things fall into place. See, this actually makes sense. Yeah, I'm gonna need these for sure when I added these functions to disable callbacks from the memory bus, and it was so that we don't stop on watch points when disassembling. I need to do that as well. So that would go in the pre in here. I can do it inside. Memory bus. Okay. Print last op. This becomes print last op, and we do that after we execute the instruction, right? Yeah. So we execute it, and then we print it. Oh, and this is actually the wrong one. It's here. Oh no, it is for step. Oh, it's because we have a number of. We can pass in n here. What happens again? We call continue execution. All right, that's how we do this. I think I'm gonna have to do this. Basically, if you ask to step more than one instruction, I won't print anything. This used to work because I would always print when trace was enabled, but I'm not gonna do that anymore. I'm only gonna have a special case for if you're stepping one instruction at a time. In that case, I will print the last op. Otherwise, no printing, and then you can use the trace command to see the last n operations. Which is fine, because we have that option now. See, that's what we used to do here as well, but we will not do it there. Oh, looks like I renamed my function here accidentally. This was what do I call it? Print last op. I would like this to be const, but I'm calling this set callbacks enabled, which is a non-const function, because I am modifying the memory bus ostensibly. But anyways, whatever. Okay, so I need to turn on trace, and then if I step, yeah, so I think that makes sense. Does it? Just wondering. Because, like, for example, here I'm at my instruction pointer is at F45E. That's very confusing. Am I doing this right? When we break into the debugger, we print the current value of the program counter. And yet, when I step, it's like when I was at F45C, that's the instruction I'm on, and yet when I step, I end up printing the next instruction. Oh, right. That's right. It makes sense. It's because the program counter that's it. I have not executed the Oh, does that make sense? This is when I realize I'm getting tired. So here's the program counter. Then we go to execute and step. I call step, we call execute. We go into execute, we say before we execute it, read the instruction at the current program counter. That's what we're doing here. And we read its operands. Then we call execute instruction, which is our CPU function. This is what then ends up advancing the program counter. All these reads that we do is what advances it. We read 1 byte to get the opcode, potentially reading 2 more bytes here. So that moves our program counter ahead. So when we're finished the execute instruction, the PC now has a different value. And we do the post-op write trace info, which modifies this trace info here with some bit more information. And then we push that back onto the instruction trace buffer. And then we call print last op afterwards. So let's see if it is doing what we think. So like I'm at F45E, right? So here I am about to step. So there's our program counter is F45E as we saw. So here we go and we say pre-op write trace info. So we populate trace info there with the instruction, which is a NOP. So let's remember that this instruction is supposed to be a NOP. We execute it. We update the trace info with the post data, and now we push back this value into the trace info buffer. And now we do print last op, which is a oh no, yeah, this is fine. It's because it's optimized, so it's kind of hard to see. So values is 1. So this reverses, does nothing. There's the NOP that we wanted. We push the NOP back. And there's the NOP. Okay, so I think I know what the problem is. It is the right instruction. It's because I'm printing the wrong thing when I print. I'm not using the program counter stored in the trace info. So it's just a printing problem. Huh, that's tricky. Okay. That's funny. It has to do with the pre and post. It's because I write the registers after we execute the instruction, and by that point the program counter has moved forward. Okay, so what we're going to do to clarify this is we're going to call this post-op CPU registers. And we're going to store the program counter Alright, Blue Dragon, thanks for hanging out. Yeah, me too, I'm getting sleepy. I'll be calling it a night soon. I'm almost wondering if I should store the state of the registers before and after. It could be maybe interesting to, like, you know, be able to show in my trace output which values were changed. Yeah, I suspect it won't be, you know, much slower. So the instruction will have the pre-op CPU registers, and we'll have the post-op and the elapsed cycles. So let's have our compiler show us what it doesn't like. So we'll copy it before and after. And then when we do the print, we'll use, for the PC, yeah, you know what? I won't do this. I'll just go directly here and I'll say traceinfo.pre .pc, and for the print registers, for now we'll do what we were doing, post-op CPU registers. Hopefully that compiles. I need to, now I need to enable trace on by default.
Give me some of that chaos control, man.
Show them how it's done, house.
Oh yeah, let's do
kick
it.
it.
Oh yeah, let's go.
Yeah, come on. I told you, we ain't even playing around here.
No sir.
Oh yeah. Give me an Allen wrench.
Give me a quarter wrench.
We gon' work that sucker to death. Yeah, give me an Allen wrench.
Give me a quarter wrench.
We gon' work that sucker to death. Give me an Allen wrench.
Quarter wrench.
We gon' work that sucker to death. Yeah, give me an Allen wrench.
Give me a quarter wrench.
We gon' work that sucker to death. Now, come on.
Not sure what's going on here. It looks like our address is moving forward, but what we're printing is always the same line. Yeah, it's like our trace is not moving forward.
Give me an Allen wrench. Give me a quarter wrench. We gon' work that, work that. Give me an Allen wrench. Quarter wrench. We gon' work that sucker to death. Yo, give me an Allen wrench. Give me a quarter wrench. We gon' work that now. Come on.
Sir J and Mr. Halsey, Dr. Ekman would like to see you in his office, like, right now.
We're close, we're close. This is so bananas. Alright, let's put a break on our step here.
Because basically, you're fired.
So we're at F4 C7. That is indeed our current PC. F4 C7, so we read our instruction from there. That should be LDA. And we store pre-op CPU registers with a value of F4 C7 here. Now we execute, that moves us to F4 C9. We go into the post. Now this here has F4 C9, that becomes our post-op CPU registers. So there's pre with F4 C7, post with F4 C9. No lapse cycles. And now we do a pushback of this trace info. Oh, what is this? I thought I had done this so that it actually pushed the values. I will not go past the front pointer. So I wrote this class in my NES emulator, and it served two purposes. So it served the purpose of feeding audio samples. So I have this, you know, for audio samples, it was for like a basic producer-consumer thing where my emulator would produce samples and the audio thread would consume them. Now, what this is showing me is that I had it so that if I produced more than I could consume, it would stop producing those samples. The samples would be dropped, which was fine for audio. But then I also used this for my save states rewind feature. But I think I didn't realize that my pushback would not move if I was full. Okay. Let me try something. I don't know what to call it. There was something also I noticed. I was returning false instead of 0. A little bit of sloppy work in here. So this is really crap there, but I'm just gonna do this thing where when we've done our pushback of n values, if we see that we actually, in fact, am I even using that one? Right, and I think this one is written in terms of the other one. It's not even. Okay, we'll write pushback in terms of just that one that works on a buffer. And then we'll have pushback move front, and we'll do the same thing. I don't really like the name pushback move front, but I'll have something different. I'll have one function where you can pass the policy, you know, should it stop at front or should it move front? And then we'll rework this. Okay, so if I got this right, and I probably didn't, but we try to push the number of values. We see how many we actually pushed. We compute the number that were not pushed. We pop that many. And then we push again, this time starting from the source plus an offset of where we actually pushed. So starting from there, push the number not pushed. Get back how many were actually pushed here. And in fact, that really should be equal to num not pushed here. And the number of actually pushed plus the number of extra pushed should equal to the number of values we wanted to push in the first place. All right, lots of checks because I'm probably going to get this wrong, and we're going to want to have a single push back, move front that takes a T-ref, right? Okay, I'm expecting to hit an assert. Well, apparently I'm pushing back and not hitting asserts, so that's interesting. Of course, I'm not really exercising a very complex case because I'm only pushing one, but let's go take a look. See, I tried to push back one, it failed because it's full, and so I get 0. So num not pushed should be 1, so I go and I pop the front. Then I try to push starting from source plus 0, so that makes sense. I try to push 1, this time I got 1 back, that's equal, and that's fine. Okay, so at least the case for that, for pushing 1 is working. And it should work for more than 1, but anyway, we're interested in that one. So now if I stop, does it look correct? Yes. See, this looks right. We can see here that, well, let's say we're in F4 D5, that instruction, and when we step it, we see the output for that line. And you know, let's say we step a few more, and if I say trace 10, we should see the last 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which looks to be the same as up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yeah. Load A, 81. Okay. Cool. So that's actually working. I should also make it possible to hit control break in the middle of printing, but anyway. Okay, that's awesome. Quite happy with that. Not sure where I should stick these guys. Here's the right place. Near the instruction and the buffer and all that. Okay, so the next thing I want to do, I have here instruction trace info. Read instruction here. I don't really have global variables in here, do I? I think it's like the only one. Usually I make these data members, but then I'd have to like expose these types. Variables. I guess I'll keep it like this for now. I'll see about moving it at some point into as a data member. I'm not too bothered by this. I'm not really gonna have more than one debugger, and don't feel like exposing a bunch of types. Peek back, push back, move front. So yeah, to address this here, I say moving, but basically it's removing. No, yeah, that's it. Okay. Just couldn't read this before, so I've got my pushback for multiple values for one value, pushback move front for multiple, and pushback move front for single. Have my pop back. Technically this pop back should be written in terms of this one. But I think this one here is not correct. So I put an assert in here. I really need to implement this one correctly, so I'll just leave it like this for now. And I have my peek back, which should be, again, the opposite way. And then finally pop front here, which only pops one at a time because I only ever needed that when I first implemented it. So despite all the inefficiencies of how this guy's working, it seems to be alright. I am going to put some notes here for these guys here. Okay, that's fine. So one thing I would like to try, now that we have this, yeah, the frame rate is totally not affected, just super cool. I'm gonna turn on trace by default in that case, because I used to keep it disabled because it was so slow. But we'll leave it on by default, so I don't have to turn it on and off. Which means that as soon as I start, now if I try to trace everything, that's 100,000 instructions, right? I don't even have enough buffer to see it. Anyway, what I will want to add is I'll want to add a way to say take that trace output and you know, spit it out to a file or something, because that'll be really useful for debugging. To spit out trace buffered trace data or trace to a file. Okay, so finally, what I'd like to try is when I try to run a ROM that throws an exception because it has, say, an instruction that's not implemented, something like that. So if I go to my ROM compatibility here, like I know, for instance, that well, clean sweep has an invalid read in cartridge address space. So let's try that one. Let's try clean sweep. Just want to see what happens. Like, is it still going to be useful? And we'll run it in release. So it's fast. All right, so here we are. We're running clean sweep. Okay, so we get an exception, right? Now, if I continue, because I have a debugger attached, that exception gets caught here. And apparently we're at this instruction, 0CDE. Now, if I just show the trace, interesting. So trying to show the trace ends up failing because the try memory, okay, no, that's okay. There we go. Yeah, it's because the debugger always breaks on that, but we can continue. Cool. Like if I print the last 1,000. Yeah, I think it's giving us an exception trying to print just the very last one. No? Like 2. It's one of the first ones here. A bit surprised. T5. So it's this load effective address here. What I find a bit surprising is it seems that it's when it's trying to evaluate this instruction here that it does that exception. Yeah, you can even see it here actually. I have this invalid read. Oh, I don't know if I can trust this. Yeah, again, this comes back to what I was saying about my comments. We can't really trust this, and trying to populate comments will go ahead and do a try read at some address here, which may be invalid, but this may not be the reason why we stopped here in the first place. It should be the instruction add 0CDE that failed us. Like if I try to step now, oh, it actually. CE1 is this. Then we're at 0CDC, exception caught, invalid vector subscript. Oh, and then we don't actually see that trace, do we? Ah, I see. Right, because, yeah, that makes sense. Because I have this try catch block here, right? And the way it works is that I'm preparing a trace info for that instruction. We execute. It fails, so it throws in this execute, and then we end up in one of our catch blocks, so we never get the chance to do the post. So what we could do is we could use a RY class here to do it for us and ensure that we add that trace there, even if it fails. The thing is, the question is, like, is adding an invalid instruction to the trace going to break, you know? Because I mean, I have to disassemble it as well, right? So I have to just make sure that disassembling something invalid doesn't, you know, doesn't do anything bad. I guess that's fine. Because right now I have no information, right? It's like totally lost. Okay, so I'm not gonna do it right now, but I am gonna put a little to-do in here. Fry or janitor class or whatever. Like what I'm thinking is our scoped exit or something. Scoped exit to make sure we call the post-op write trace info and push back, so that if an instruction, so that if execute instruction throws, we have the instruction in our trace. Okay, let's see what our diffs look like. Yeah, we definitely changed circular buffer a lot. But this is actually a new file, so whatever. So let's look at our debugger. So where all the work was done tonight. Circular buffer, speaking of a pointer. Yeah, lots of changes for the fact that we changed CPU op from a reference to a pointer. So that's a bit of noise in our diffs here. One thing I can do to get rid of that noise is, this was nice about Beyond Compare, is we can say add as unimportant text, and we'll say wherever you see CPU op arrow, and then we can say, like, we can see all the blue, that's now considered unimportant. If we were to hide that, well, yeah. It's okay, I'll leave it like this because at least I know that if I see blue in there, it's most likely that's the reason for that diff. Because I may have some actually invalid changes where I'm doing that, and I don't want those to be ignored, those lines to be ignored. So print op now accepts instruction trace info. Yeah, disassemble. You merge those together. Okay. That's our new. I'm not super happy with the fact that I have T and trace. I think the real problem I have right now is that trace and color are these toggles, and I probably want to change it so that I have like a toggle command. So I have a toggle trace, toggle color, and then after that I would just use T and trace to do the output. So I'll do that at some point. And finally that's gone. Cool. Looks good. So. Store trace data in memory in circular buffer and add new command to print the last n instructions. As we only disassemble ops on demand in the debugger. As we separate collection of trace ops from disassembly. The latter is only done on demand in the debugger console. Note the comments section of the trace of the instruction trace output cannot be trusted or is invalid. Valid as it reads addresses. It reads from as the contents may have changed when the instruction was the comment section of the instruction trace output is invalid when reading from memory as the contents may have changed since. Okay. Okay, so I'm going to push that, and I will add also I guess it's all like trace, you know, debugger trace. I suppose this one isn't really. So I just want to put here for debugger trace. How we can look at how we can fix the comment part of disassembled. Okay, well, I've pushed the changes and I'm pretty happy with what we've got. So guys, thanks for watching. I'm gonna head off, and if all goes well, I should be streaming again next week on Monday. So thanks for watching, and hope to see you next time.